Good afternoon, everybody, and welcome to your AP Physics 2 live stream for our very last lesson. Mr. Eaton and I are delighted to be here with our guest today, Emily Calandrelli, a brilliant science educator, a science advocate. You've, I'm sure, seen her show, Exploration Station. Emily, we are delighted to have you here today, so welcome aboard.
Thank you. I am very excited to be here.
Well, we have a couple of questions for you. We couldn't resist asking. I hope you will indulge us those questions.
Yep.
So you have so many science accomplishments under your belt. You've done an impressive amount of stuff at such a young age. Why don't we begin with just you telling us a little bit about your own educational and professional journey?
Yeah, sure. So I am an MIT engineer turned science communicator. So I have a TV show on Fox called Exploration Outer Space. I am on the Bill Nye Show on Netflix called Bill Nye Saves the World. I have a series of children's books called The Ada Lace Adventures. I've done YouTube series for Lockheed Martin and for Discovery, and I have my own YouTube channel now. And then I have my own show on Netflix coming out in a few months called Emily's Wonder Lab, which I'm really excited about. But all that to say, I started out, I would say, not really considering myself one of the smart kids when I was in high school. I grew up in a college town. And so the smart kids at my high school were the kids who had parents who were professors at the local university, parents who had PhDs of science and engineering. And like, I didn't know anybody in science or engineering. And so I just felt like I wasn't one of the smart kids. But when I was looking at what I wanted to major in college, I knew that I enjoyed math. And I knew that I wanted to get a good paying job at the other end. And so I literally like Googled all the majors that one could major in and looked at their starting salaries. And the starting like the highest salaries were, consistently engineering majors. And so I was like, okay, well, I'll do engineering. It's going to suck. Like it's going to be 4 years of just suck. But then afterwards, I'm going to have a good paying job. But along the way, I learned of all of these things that slowly made me more excited and passionate about the stuff that I was studying. And so things like if you're an engineering major or a science major, you have really cool opportunities to work on meaningful and interesting problems. Like I was part of Engineers Without Borders at West Virginia University, and then I did something called the Microgravity Research Team, where I developed an experiment to fly on NASA's Vomit Comet and float like an astronaut. You can travel the world with paid internships, which is, sort of unique in college. And just like the fact that if you're studying engineering, even if you're not sure if you want to be an engineer, like consulting firms and business firms will want to hire you because it's just a sign that you can work on hard problems. And the fact that like if you are studying science and engineering, you are likely going to be able to go to grad school for free, which is not the case for a lot of different majors. There's just a ton of fellowships and RA-ships and stuff that you can get to go to grad school for free. So I came out of school with no student debt. Wow. But anyways, all that to say, I started at West Virginia University majoring in mechanical and aerospace engineering, and then went to MIT to study aeronautics and astronautics, and then something called technology and policy. And then after graduating, I got a call from a production company that was like, would you like to be the host of a TV show about outer space? And I said, yes, that sounds amazing. And that was 7 years ago, and have tried to build my platform ever since.
Well, since you began on that show, you've explored so many things. You've taken viewers on fascinating journeys through outer space. You've had the opportunity to work with folks from NASA on several of their projects. Since physics is integral to space science, can you talk about some of the things that you've learned through your work that our AP Physics students ought to know?
Yeah, so physics, as you can imagine, is at the heart of like so many things in the space industry. But I'll talk a little bit about a couple of things that I have found really interesting that I've learned. And one of them is how satellites communicate things back down to Earth, because every satellite in space is collecting some type of data or transmitting some type of data, whether it be pictures or imagery or just information from one part of the globe to another. And they communicate back down to the Earth using the electromagnetic spectrum, using radio waves. But what I found really interesting is that when I'm thinking of like there's 2,000 operational satellites in space, when I'm thinking of someone sending a satellite into space, I always think the bottleneck is like the physical space. Because you watch the movie Gravity and you see satellites colliding into each other, and it's this domino effect that creates this terrible collision. But really the bottleneck isn't physical space. There's a lot of space in space. But the bottleneck is the frequency, the radio frequency that you want to communicate with, that you want to transmit your data with. That's the limited resource. So there's this international body called the International Telecommunication Union that regulates who gets what frequency in outer space. I love things that intersect science and policy. So that I found really interesting. Another thing that I learned that I really love is Kepler's laws of planetary motion. Just the fact that we can bring order to the magnificence that is the solar system, I find really weird and wonderful. And there's 3 laws, but the second one is the one I find really cool. And it talks about how planets sweep equal areas over equal times. And I have a diagram here that I find interesting. So this is the sun and this is, say, Earth. And when you have an ellipse, there are 2 different foci, there are 2 focus points, one of which the sun is at. And so it sweeps equal areas, meaning like this is an area and this is an area over equal times. And for us in the Northern Hemisphere, we experience our winter when the planet is closest to the sun. The axial tilt creates seasons, not our distance to the sun. But when we're closest to the sun, that's our winter, and it's moving faster. So it's actually moving like 2,000 miles per hour faster during our winter than it is our summer. And so I like to think of the Earth as like slowing down during the summertime to enjoy the summer a little bit longer for us in the Northern Hemisphere. And so we get like a couple more days of summer. And then the last thing that I will say that I find really cool is that the Earth is a magnet. We have like our outer core is this like molten material that is carrying current. And because our Earth is spinning, we have spinning current, which is creating Earth's magnetic field. And that magnetic field is one of the reasons we have life here on Earth, because otherwise the activity from the sun would just strip our atmosphere away and we wouldn't be able to have life here as we know it. But the other really beautiful part of the magnetic field is that it directs the solar activity to our north and south pole, which creates the auroras that we see, which I think is really cool.
Yeah, without Earth's magnetic field, we wouldn't have any way to deflect those particles coming from the sun. It really keeps us alive. So you studied science and policy and the intersection of those. So you certainly recognize the valuable link between STEM education and solving big humanity-sized problems. Our students are just now learning about the big ideas in physics: motion, forces, energy, momentum, light, heat, and probability. Hopefully, they will come to understand how they can use what they've learned to solve community problems. Can you talk a little about how important and exciting it is for doing this kind of work in the field of science?
Yeah, and just like to rewind a bit, I think it's really valuable to question whether or not what you're studying provides value to your community. I think that is something that maybe people should be asking and thinking about a little bit more. And I really love that, some people are already thinking about that. I will also say that something like physics that helps expand the knowledge, the base of knowledge that humans know, is in itself beneficial, right? We don't necessarily need a technology to solve a problem for the science to be beneficial to our community. Just that's kind of what makes humans human, right? We understand how the universe works and what our place is in it. And I think expanding that base of knowledge is just inherently beneficial to a community, to the community of humans. But I think it's also really interesting to think about the fact that physics is an enabling piece of knowledge. It's like an enabling platform from which to build technology off of. Because any type of technology that has brought value to humankind has, if you think about it, started with our understanding of physics and science and how something works. So things like GPS satellites that the government uses or that we all use every single day on our smartphones, or satellites that help bring healthcare information to communities that don't have hospitals, or that bring educational materials to areas that don't have proper schools. Or just any other technology. I'm thinking of space-based technology, of course, but like any other type of technology that you can think of that provides value, that was first designed and thought of because of our understanding of things like physics. And I think when you are expanding that body of knowledge, you are creating a larger platform from which technologies can be built from. And that, I think, is obviously incredibly valuable.
Thank you very much. So in my household, we are big fans of exploration outer space. I know that I have some of my favorite moments from the show, but I've got to ask. This is really exciting for me. I'm a little bit starstruck. What was one of your favorite moments? Maybe a scientist that you got to work with, a place that you got to go. What's on your like top list?
Oh man, I've definitely had more adventures than I've been so lucky because as a space and science nerd, like I've been able to talk to some of the coolest and smartest people in the world and just ask them any question I want, which is amazing. One of the adventures I had last year was really fun. I got to go to CERN, which is in Switzerland and France. It's the home of the Large Hadron Collider, which is like this incredible, I think it's a 16-mile circumference loop where they accelerate particles near the speed of light and run them into each other to try to understand how the smallest particles in the universe, like to understand what the smallest particles in the universe are, and more things about how the universe is just made and operated. And I think that is really cool and fascinating. And I was able to visit this location in Switzerland. But before I went, they were designing my tour and they had asked me just like a few really run-of-the-mill questions, like, do you have any mobility issues that we should know, or any health issues? And by the way, are you pregnant? And at this point, I was 6 weeks pregnant, very, very early in my pregnancy. And for people that don't know much about pregnancy, typically you wait a few months to tell anybody about the pregnancy just to make sure that everything is okay and healthy. And so I wasn't telling anybody about it, but because I was going on this tour, I had to tell them, because a lot of the experiments that they do at CERN are in an environment where there's a little bit of a higher amount of radiation. And so they just want to make sure that everybody's being very safe. And so I had to reveal to them that I was 6 weeks pregnant. And then when I went on this tour, I met a lot of physicists who were telling me about their experiment and then were like, by the way, congratulations. And it was like, oh, nobody knows about this, but thank you. And so at one point in my pregnancy, the only people who knew that I was pregnant was me, my husband, our doctor, and all of CERN.
And a 16-kilometer ring of scientists.
Yep, exactly.
Wow.
That was a really fun. I mean, it was a wonderful trip, and my brain hurt afterwards by thinking so much about the universe. And I was like, all of this to understand. But it was a really great trip. The other fun thing that I did recently, just a few months ago, was I was able to tour the LIGO facility in Louisiana.
That's so cool.
I know, it was so cool. So LIGO is the largest project that the National Science Foundation in the United States has ever funded. And it is the facility, there's one in Louisiana and one in Washington State. And it's a facility that's responsible for detecting gravitational waves for the first time in, I think, like late 2015. I think they announced it in 2016. But it was so cool. So the way it works is that there's like 2 4-kilometer arms that are perpendicular to each other, and they are measuring like they were measuring ripples in space-time by shooting light down each of the arms. And because we know the speed of light, we can tell if one arm got shorter and one arm got longer, which would indicate a gravitational wave. And they know how to account for like other types of ripples that might happen, like from earthquakes or just like ocean activity or animals in a field where they're stomping and creating these waves. But anyways, it was really, really cool to be able to actually, like, I went in one of those arms to look down a 4-kilometer arm and be like, history happened here.
That's amazing.
It was so cool. And like, I mean, gravitational waves are inherently really incredible because it gave astronomers an entirely new way to study the universe. Like it's like inventing a telescope for the first time and being able to look at the universe. And now we've developed this entirely new technology to study the universe. Like we've invented another thread to pull at to see what the universe is telling us and unravel the mysteries of what's happening in this universe that we live in.
It's just incredible. We spent 400 years looking at the sky with telescopes only to finally realize it's been singing to us the whole time. So
ooh, I love that analogy. That's great.
So we know that one of your lifelong passions has been to encourage young women to be interested in STEM. If our nation is to increase its pool of engineers and researchers and scientists, so we can find solutions to these big real-world challenges, young people must believe that they can pursue a life in science. What advice do you have for the young women watching who may be thinking about pursuing a STEM career?
Yeah, so I mean, I think the major point here is that when we are designing as engineers and scientists, when we're designing products and technology for everybody, then the people behind those products need to come from all sorts of backgrounds because humans are biased, either subconsciously or consciously. And so the way that we design technology will also be biased. And so things like artificial intelligence or different drugs that we might create or the safety of cars. There's this story of like, they were using these test dummies that were designed after the average male in car crash tests to make sure that seatbelts and cars were safe for humans. But it wasn't until 2011 that car manufacturers were required to also use a dummy for the average female. And so cars made before 2011 aren't designed to be safe for women, and women as an effect of that had like higher injury rates and higher death rates in cars. And so it just speaks to the importance of having different people in the room, at the table, behind the computer, in the lab with different backgrounds so that we can think of these issues when we are designing technology in the beginning. And speaking from a more female perspective, one thing that I was considering maybe when I was in high school was that I couldn't bring my creative side to science and engineering. That was the assumption that I had made because I loved art and I loved writing. And I was like, well, these are going to be parts of me that I'm going to have to leave behind. I originally thought that I wanted to go into architecture because I thought that would combine my love of math and art really well. But my college didn't have an architecture program. So I was like, I'll do engineering for now. But what I've learned since is that if you do bring your creative side with you, you can create something uniquely special in this world. And the people that I look up to the most are the ones that are really creative and they combine that with their love of science. So people who are really great science communicators, for example, if you are on Instagram, people like Science Sam or Science Bay or Hood Naturalist or Stephanie Explains It All. These are women who are incredibly creative and great storytellers, and they combine that with their love of science. So that's the other thing. That's the one thing I would say is that don't be afraid to bring that with you, because then you'll be able to have this like unique attribute to bring to the field. And then the other piece of advice I would give to women is that make friends with other women who are going through the same thing. Because for me, when I was an undergrad, I was one of maybe 2 women in a class of 50 in different engineering classes. And when you walk into a room and everybody is different than you, it can make you feel like, I don't know, maybe you would walk in and you don't have as much confidence as you normally would. And so being able to reach out to other women going through the same thing, it makes you feel less different and like you're going through this with a group of, with a community of people. And it just gives you more confidence to bring your voice to the table. And so that's the other thing I would say, is just make a solid group of female friends going through the same thing.
Thank you.
Awesome.
Thank you very much for that advice. Listen, I know that we're running a little bit over your time and that your time is truly precious. However, as a fan of your show, I am told that you an email was successfully relayed to you, and I am wondering if you maybe brought the motor that you made on your YouTube channel about 2 weeks. It's right there. I'm just wondering if you could maybe talk our students through what it is and how it works. It does pertain to the curriculum that we are working on.
Yes. So let me get my
Oh my goodness
workstation ready here. This, as you can see, I don't really have the best facility and my equipment to be doing these things, but let me show you. So this is an example of the Lorentz force. And the Lorentz force is this force that's created when you have a current carrying wire in the presence of a magnetic field. And so you can create a very basic motor using this principle, which is super fun. And let's see, so this is a magnet. And the only thing that's hard to tell is what end is the North Pole and what end is the South Pole. So it's kind of hard to know which end is where the magnetic field is going, whether it's going this way or this way. This is our battery. And so you just connect your battery to your magnet like this, and then you get copper. Copper is conductive. It has free-flowing electrons in it. There's like a sea of electrons moving through this, which makes it a good conductor. And so what we're going to do is essentially create a closed circuit by touching our copper from the top of our battery to our magnet. And when we do that, we are going to have a current carrying wire in the presence of a magnetic field, and that's going to create a force on our wire. And so I can show you this right here. Ta-da!
Look at that. That's amazing.
The hardest
awesome.
part is getting it to balance. I'm telling you, it takes like hours to get it to balance well. And once you do, it's just like, oh my gosh, I've created a beautiful thing. But you can actually predict what direction it's going to turn in using the right hand rule, which, Joe and Brenda, did you say you already went over this? Is this something that you've talked about?
We did indeed.
Mm-hmm.
Awesome. So the way that I have learned it is that your thumb is the direction of current. And I think the conventional way of thinking about current is going from positive to negative. Is that right? Even though electrons.
That's right.
Okay, conventional way. So we're thinking the current is going this way through our wire right here. The magnetic field is going, let's see, it's like really hard to think about this and talk at the same time. It's like chewing gum and patting my head or something. So it's moving this way. So let's see here. So our magnetic field must be going from north to south. Is that right? This must be the north end. This must be the south end if it's moving this way. And so right hand rule, our thumb is the current. Our fingers are the magnetic field. And then the direction of your palm is going to be the direction of the force that's exerted. And so we think about it this way. The current is moving down this way. The magnetic field is going, oh wait, it's going which way? Oh no, it must be the other way. It's going.
Yeah, I believe south is on the top of yours.
Yeah, south is on the top right there.
It may also be flipping the video, so it's a little hard to tell.
Oh, true. But the fun thing, the other, just to kind of cap this, what's interesting is that if you switch your magnet, so you switch the direction of the magnetic field, you can make it go the other way. And this one, it's less balanced for whatever reason, but I can show you with my little dancer. It will move the other way, which is really cool. So now it's going this way. Yeah, so that's the Lorentz force.
Wait, and that is the science of the Lorentz force.
And that is the science behind the Lorentz force.
Oh, that's so cool. So thank you so much, Emily. It has been an absolute joy to have you on the live stream.
Thank you for having me.
That
This
was
was very
wonderful.
fun.
Thank you so much for agreeing to this.
Oh my gosh, this was such a fun thing to prepare for. Just thinking about physics and space for the last like 48 hours has been like not a bad time.
It is a pretty good way to spend your time. Well, students who are watching, definitely look up Emily, check out her show, check out her YouTube, check out her Instagram, check her out on Twitter. You are going to learn a lot of science, and it is going to leave you saying, wow, and the world will just never look the same to you again. So, Emily, thank you very, very much for joining us.
Yep, thanks for having me.
Thank you so much.
Thank you. All right. So, ladies and gentlemen, I'm going to switch us over to the presentation over here. And bear with me one moment. There we are. So, for today's lesson, we'll just be closing out electromagnetism with solving problems in magnetism. As always, we'll work through a lesson overview. We'll do our daily warm-up, talk about what you need to know, work through some guided practice, a quick debrief and summary, and leave you with a question for tomorrow. I'm still Joe Mancino. I'm still from Glastonbury High School in Glastonbury, Connecticut. My compatriot here will introduce himself. There we go.
I've been Eaton from Reedy High School in Frisco, Texas. And as usual, this is kind of a sad day. We're going to look at the course map of all the reviews that we've done up to this point. And we are at the very last item, which is, it says electromagnetic induction, and those are the problems that we're going to go over today. We're going to try to give you as many problems as we can in the short amount of time that we have left. And we hope that you enjoy all of them. And if you need to, take a screenshot of this, and that gives you an idea of all the hot topics that we covered for our review courses, and go back to YouTube and check out the ones that you know you have the most trouble with, and take a little bit more time on those. Pause the video when we give you a question to work on, and try to work that out from scratch without looking at notes and that type of thing. And yeah, so it's all there. Go out and enjoy it. It's going to be amazing.
So, as Mr. Eaton said, this is the end of the review content, but it is not goodbye. We will still be joining you for AP Prep Week next week. More to come. Here's our goal for today.
All right, so we need to give you some information about the exam, starting with Prep Week, talking about checklists that you need to make and or keep track of as you go through this process, the items that you need to bring with you for the AP exam and taking that exam. And we will also discuss the format and the timing and what to expect for the AP Physics 2 exam this year.
All right, so by the end of this lesson, we want you to know what's coming up on the exam and how best to prepare. And we definitely want to make sure that you can approach the questions that you might encounter about magnetism and induction. So we're going to start with the warm-up. That's just working through yesterday's work. Your first mission was just, can you around a magnet, show which way a compass would point. Draw an arrow to show the orientation of a compass needle at each point. The arrows are drawn on there. Magnetic field, just like Emily said, is out of a north magnet and into a south magnet. Speaking of which, the follow-up to this was about a moving bar magnet. Now, I've redrawn the diagram with a more clearly labeled north and south, and you'll see that magnetic field points out of the north end and into the south end. But in this question, it was about a magnet moving into a current carrying or a conducting ring. It didn't initially have any current in it. So there's the ring. That's our gray ring right there. And I'm going to click to start to bring the magnet in from the right of the screen. It comes in south end first. So there's the magnet, and you can see the magnetic field pointing left, right towards the south end of that magnet. Moving the magnet closer to the ring increases the leftward flux through the ring. If increasing that current, if moving the magnet closer creates a leftward flux, then the current will make a rightward flux. In order to make a rightward flux in that ring, well, put your thumb in the direction of current. It's this right-hand rule where your thumb is in the direction of current and your fingers curl in the direction of the magnetic field. If you were to grab that ring with your thumb right in the ring of it, your fingers would curl through the middle and point to the right. opposite the direction of the field from the magnet. Now, as the magnet moves through the middle of the ring, the current changes direction. So the current is momentarily zero as the rate of change of the magnetic field goes down. In the middle of that magnet, the field is pretty uniform, so the change is not going to be very quick. Now, pulling the magnet out of that ring means that the magnet is decreasing the leftward flux, so the current in the loop makes more leftward flux. Remember, the direction of the induced current is to oppose the change that caused it. And here is what you need to know for today.
All right, so we'll start by talking about preparing for the AP exam, specifically that prep week is next week. And let's discuss, or at least get you thinking about your plan to take the test. Now, as far as induction is concerned, we need to recap that when flux through a loop of wire changes, the current is induced in a wire to basically counteract that change in magnetic field or change in flux. And the magnitude of the current does depend on the rate of change of flux, and the direction of that current depends on Lenz's law. All right, so here it is. Next week is AP prep week for all of your courses. It's the week before the actual exams start beginning for all the courses. So you have the opportunity to get out there and check out every single one of those AP courses that you're taking and getting that final last little push of review. And specifically, this is what our schedule looks like for next week, May 4th through May 8th. On Monday, we'll be proctoring. Well, I hate to use the word proctor, but we'll be setting up a full exam for you. So you'll have 25 minutes for a QQT type problem, a qualitative quantitative translation, and 15 minutes for a paragraph length response. And after that time is up, you'll get some tips from us on starting and ending and all that good stuff. We're about to give you some of those right now too. Tuesday, we will actually go over those questions that you worked on Monday. You're not turning it into us, but you're saving your work and bringing it back, and we'll discuss it. Wednesday is very similar to Monday, except with 2 new questions that you haven't seen yet. Thursday, again, goes over the questions from Wednesday. And Friday, Mr. Mancino said he was going to wear his Hawaiian shirt again on Friday, so I hope that you show up for the Hawaiian shirt.
It's going to be a luau.
All right, so what you need to do to prepare for the exam is you need to practice the testing environment demo at cb.org/AP demo. And hopefully take a screenshot of that so you can type it in later or write it down on a piece of paper. But hopefully your teacher is sending that information out to you too. So you've got a couple of different places that you can find that information. But I know that you can see it directly from the College Board's website. So get on College Board, figure out how to get to that practice exam environment. So on May 11th, you'll get a ticket by email for your exam. And the exam will not work in Explorer. So think about the options that you have. And I believe that Chrome and Safari is perfectly fine to take the exam.
Yep.
Now you need to know 2 good ways to submit responses. And I think Mr. Mancino has some good words for submitting those responses.
I do. I know that there is a lot of uncertainty out there in terms of how you're actually physically going to answer these questions. Now, I can speak for the AP Physics 1 and AP Physics 2 exams, so please don't take my words out of context and begin to think that they apply to other exams. Look specifically at what the College Board has to say. What I can definitely say is that as a member of the AP Physics 1 Development Committee, we wrote all of the questions so that in a worst case scenario, they could conceivably be answered on a cell phone or a tablet. You will not have to draw any figures or diagrams. You will not have to plot points. You will not have to graph curves. You will not have to do any kind of algebraic manipulation or even write an algebraic equation down. You will not have to do any of that. Every single question can be fully answered in prose, in words, just in almost like a transcript of the words that you would say. That is sufficient to fully give a full credit answer to any of the questions. Now, that being said, some of you are still going to want to write. If you aren't a great typer, if you know that you're a fairly slow typer, if it's just challenging for you to type, if you have a cramped keyboard, you don't want to type, you want to write, and that's fantastic. Please do that. Do whatever's most comfortable. But make sure that after you've written during the 5-minute upload window, that you have a really, really solid plan and a good method for getting a good, well-lit, high contrast, clear photo of your written work. And somehow uploading that, getting it to the device on which you are taking the exam, and sending that to the College Board. You can practice doing that at cb.org/apdemo. Practice it now before test time. The second way to submit responses is to type them into a document. And once your answers are typed, and you can fully give any answer in a typed response. Once your document is typed, you have the option of, if that document is a Word doc or a PDF, you can attach that document to your test. So it'd be like sending an attachment along with it, and only text will send. You can't add pictures to your document. You can't insert equations using an equation editor. It's only text characters. Your other option is to copy what you've written and paste that into the College Board's software. You can't type in the text boxes on the test. Try it out for yourself at cba.org/apdemo, but you can copy and paste into the box. If you paste something and want to change it later, there's a button to clear your response. So while you're taking the exam, you'll have a timer at the bottom of your screen that'll tell you how much time is left. Now that's the total time to give your answer and submit the answer. Once that timer gets under 5 minutes, the text will turn red. You'll see a pop-up reminding you to stop working. You only have 5 minutes to send in your answer. Copy and paste your work, attach your document, whatever you need to do, and then hit submit. If you're not done, stop. You can definitely still earn an outstanding score, even if you've left some questions unanswered, even if you haven't gone back and dotted your I's and crossed your T's. If you don't submit your response on time, it cannot be accepted. It will not be accepted. There is no way to send it in once it's too late. You will not receive credit for it. It is better to send an answer that you're pretty happy with, but not delighted with, because something is better than nothing at that moment. Losing track of time and not submitting a response before time runs out is not an acceptable reason for requesting a makeup test. Please send in what you have. The AP readers have just gotten some invitations, and they are very excited to score your exams. After the exams are scored, AP will set standards for scores of 3 and 4 and 5, so it's not more difficult to earn those scores this year than in prior years. This exam will be scored with just as much fairness and just as much fidelity and just as much thoughtfulness and care as we have always given it every single year that these tests have been administered. The structure of the test has been publicly announced. I think we've said it here a few times. There's a 25-minute QQT. We've discussed what that is. A 5-minute upload window, a 15-minute paragraph question where you have to give a full and thoughtful answer containing a good chunk of text about how and why certain things happen, and then another 5-minute upload window. So the total time that you will spend working on physics is 40 minutes, and then a total of 10 minutes uploading, but it will go in that order. You won't see question 2 until 30 minutes after the test begins. You won't see question 1 once question 2 begins. All right. So we're going to very quickly talk about magnetic field and induction. Remember, induced EMF is the negative rate of change of flux. What that means is the faster the flux is changing, the more voltage is induced. And that negative sign, living in that little negative sign, is all of Lenz's law. All right, so here is one quick example. There's a wire carrying current from left to right. The direction of the magnetic field is drawn. There are dots showing a field coming out and X is showing a field coming in, but the current in that wire is going to change over time. Now I've color coded the currents here. The black graph refers to the black wire. Which of these blue graphs shows the magnitude of the induced current in the blue wire over time? I'm going to repeat that. There are 3 graphs of the magnitude of the induced current, not necessarily the direction, just the amount of current. If this were on an ammeter that only read magnitude, which of those graphs would show the magnitude of the current in the blue wire as a function of the same t-axis of time? So the induced EMF is equal to the rate of change of current, is equal to the rate of change of the magnetic flux. So the changing current in the black wire causes the flux through the loop of blue wire to change. Now, what you'll notice is initially the bottom left graph of the current in the black wire as a function of time is steep. That current is changing rapidly. And because the current is changing rapidly, that means that there's a rapid change in flux in the beginning. And then when the current is highest, there's no change in flux. And right there, that should be your clue. In that middle time range where the black graph is flat, there's no change in flux. Now, I know that that's where the current is highest, but there's no change in flux. So it's definitely that second graph. So we're going to take a second look at this with this time a magnetic field that changes in time. So I've drawn the same setup. You see that I've labeled B for the magnetic field, and that blue box is just a resistor. And we see that the magnetic field as a function of time is defined by that graph. The magnetic field is initially positive, then it becomes very negative, and then it kind of becomes less negative. So at which marked time, T1, T2, T3, or T4, is the magnitude of the induced current in the blue wire the greatest? Well, the magnetic field is positive at T1. The magnitude of the magnetic field is greatest at T3. But you clever AP Physics 2 students, you know that it's not the magnitude of the field that determines the induced EMF. No, it is the rate of change of the flux that determines the EMF. So at T2, that's where the graph of magnetic field versus time is steepest. Okay, in this question, it's another rail problem question. That's usually how these are referred to. But this one has a bar on a tilted set of rails. And as that bar slides down the ramp with negligible friction, the two ends of the bar are resting on conducting wires that are also in a magnetic field, as you can see in the diagram on the right. And we see that there's a little light bulb connected to a wire bridging those other 2 bars. And my question to you is, what is the direction of the induced current in the bar? Well, for that, we use the right-hand rule. I've got a magnetic field pointing right out at me, and I've got the bar moving to the right. So the magnetic field is towards me, the bar is moving to the right, which means there is a downwards current. A downwards current in the bar means a clockwise current in that loop of wire. All right, now Mr. Eaton is going to take you through some guided practice problems, which are unsurprisingly all about magnetic flux.
There you go.
Induction.
All right, so here's your first question. This is really similar to the question with the graphing that Mr. Mancino just went over, but I want to point something out super quick. On the given graph for the wire, which is in the bottom left-hand corner of your screen, notice that that is no longer the absolute value of current. So if it's not the absolute value of current, we got to think about that negative sign from Lenz's law to help us determine what that graph is going to look like. So we remember that the slope of the I versus T graph is going to tell us what that magnitude of the induced current actually is. So looking at from time 0 to 5, I guess if you count all of those little boxes across the bottom and say that's 0 to 5 seconds, we have a constant slope. And if we have a constant slope, we should have a constant value for the current at that point in time. But remembering what's in Lenz's law, that negative sign needs to be applied in this case. So that narrows that down to the top choice and the bottom choice as far as what that current is at that point in time. Mr. Mancino, you're making a funny face at me.
I was just thinking about the bottom choice. So remember the current in the induced current in the second wire is going to have the shape of the slope of, or the negative shape of the slope of the current in the first wire. So in the second wire, we have to remember that the direction of current is going to be opposite the change that caused it. So in the black graph, I see a constant positive slope. So in the blue graph, I want to see a constant negative value for the first time period. In the black graph, for that middle time period, I see a constant negative slope. So in the blue graph, I want to see a constant positive value. So that top graph is a really solid candidate. And let's advance to the next slide. There we go.
You had me worried. I thought I was saying something wrong. That's where I was going with that. All right, so here's the current induced in a bar that Mr. Mancino kind of went over already, but what's different about this particular question? It says current is flowing downwards in the bar. What is the direction of the magnetic force on the bar? So on the previous, on the one that he already went over with you, it says the bar slides down the ramp with negligible friction. What's the direction of the induced current in the bar? Well, downward with negligible friction probably meant that it was speeding up. And I think that this is probably still negligible friction as well. Is that the same setup for this, Mr. Mancino?
That is the same setup.
Excellent. So we know as the bar is sliding towards the, what am I trying to say? Light bulb, the flux that's going through that loop, the flux is decreasing throughout that time. So if that flux is decreasing, I actually teach my students a different way, and I can't teach you it because I don't want to confuse you. But if flux is decreasing, that means that negative delta phi delta t turns into a positive value for EMF. And if I've got a positive value, I know that the force on the bar, I got to think about this for a second. Mr. Mancino, what do you say?
Well, I say that the current is moving down in the bar. And if there's a downward current in an outward magnetic field, the force is to the left. Or you could say that the force that's causing the change is rightward or down the ramp, which means that the force experienced by the induced current is in the opposite direction. Lenz's law tells us two things. The induced current flows in a direction to oppose the change that caused it, and the result of the change will be a resistive force. Causing a change in this bar, moving the bar down the ramp, causes the bar to experience magnetic force up the ramp. Nature opposes change.
It's crazy how that works. All right. This is the last question that we have for you. And if we have time, we can show you a really awesome demo that we have. I'm not sure if we have time though. Let's check out this wire loop that is in a magnetic field. And I brought one of these just so you knew exactly what Mr. Mancino was talking about a couple of lessons ago. If you have a roll of masking tape, put it in your room where you're going to take your test. You may need it to help you determine the direction of current. All right, so if you have the wire loop and it's rotated in a uniform magnetic field about the axis that's perpendicular to the field as shown. So notice where the axis is. The axis is running horizontally and your wire loop is sitting like this, and the magnetic field is pointing in the plane of the screen that you are currently staring at. So how many times is the induced current in the loop reversed if the loop makes 5 complete revolutions from the position shown? So a lot of times it's just wrapping your head around what the problem is telling you is actually happening. So if this thing is rotating about the axis, this is what that would look like. Bam, 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 bam. But before I go any further and try to make some calculations, this is strictly about concept. When the loop is situated just like this, is there any flux through the loop? And your answer should be no, because the magnetic field is parallel to your page. So as this thing rotates, flux increases, flux is decreasing. That's only a half of a rotation. So flux is increasing, flux is decreasing, right? That happens twice. I'm sorry, it happens twice per full rotation. So When it's asking you about the current reversal, that's happening twice per rotation. So what you see on your screen is in one rotation, the flux increases, decreases, increases, decreases. That gives you 2 current reversals per full rotation. So if this thing rotated 5 times, that means your current is reversed 10 times. So again, if you have one of these laying around your house, which I'm sure you do, or something that resembles this, grab this, put it on your desk, have a great time.
Okay, well, as much as we would love to show you this demo on electromagnetic induction, I think it's something that we can safely save for perhaps a quick 5-minute session on Tuesday. We're going to run through a very, very fast debrief and summary. When the flux through a loop of wire changes, current is induced in the wire. The magnitude of that current depends on the rate of change of flux, and the direction is determined by Lenz's law. Whew.
And can that's a lot. That's a whole lot. Can you answer these questions? How does regenerative braking work in electric vehicles? Look it up. It's really cool. And how do pickups in an electric guitar know how fast the strings are shaking? Again, something I would highly recommend looking up. Awesome applications of magnetism.
Speaking of awesome applications of magnetism, what is a mass spectrometer anyway? It measures the mass of individual atoms or molecules based on the radius of the curve they take as they travel through a magnetic field. So this is a mass spectrometer. Some kind of voltage source maintains an electric field between 2 parallel plates. There's the electric field right there. And as you see in the dotted line, charged particles are launched into the region between the plates, and they exit and then curve through a magnetic field to a collector. What we didn't show on here was there is a separate way that the charges are created with an accelerating voltage. So some kind of accelerating voltage gives some QV to those particles, which gives them some 1/2 MV squared as they move through the region of electric field. But why do they move straight in that region of electric and magnetic field? That's weird. I thought both of those fields would cause curved motion. All right, so here comes the actual question, the thing that you're going to have to take a screenshot of. Particles are projected into this apparatus. A battery connects the parallel plates. The particle in the diagram moves with constant speed around that circle, and if the mass is just right, the particle is able to pass through the small opening. So grab a quick screenshot of the setup. There's a screenshot. So write an expression for the accelerating voltage. And once you've written that expression for the accelerating voltage, can you explain how the particle is able to pass through that region in a straight line? And once you're able to, so grab a screenshot of that one. Once you know why the particle is able to pass through that region in a straight line, what must the sign of that particle be? Notice the way that it curves and the direction of the electric field. What must the sign of that charged particle be? Now, your clues are going to come there from region 2. Finally, in region 2, what is the radius of the circular motion of that charge? How would you even find it? Alrighty, folks. So thank you very, very much for watching. We hope that you join us next week for AP Prep Week. Mr. Eaton will take you through an exam question on Monday. I will take you through an exam question on Wednesday. The two of us will team up on Tuesday and Thursday to talk over all the details of those questions with you. Both days we'll have a QQT, a 5-minute break, and a paragraph question. So 2 essentially full-form practice exams for you. We look forward to it. And then Friday is our grand send-off. And then you will be super prepared and very successful on the exam on May 13th. It has been an honor being able to work through, in these very strange times, some very interesting material, and I hope that you stay with us for next week. Have a great weekend, everybody.
Yeah, we really hope that you guys have found a little bit of a comfort in joining us every week, and thank you so much again, and just reach out if you guys think that you need anything, and we will see you Monday for a full form test. Get some rest.